Okay, everybody, welcome to the latest FlightGlobal's sustainability webinar, the first of 2023. And like 2022, we'll hold 4 across the year. And as ever, they'll be available to watch on the FlightGlobal.com website at your leisure. My name is Mark Pilling. It says so right there. I got it. I'm a contributing editor at FlightGlobal and your moderator today. Now, we're partnering with our webinars in 2023, once again with Pratt & Whitney, and it's my pleasure today to welcome Vince Sidwell, the Director of Advanced Concepts and Technologies at Pratt & Whitney, to the panel. Welcome, Vince. Great to have you with us.
Thank you. Nice to be here.
Great. Thank you. And we also welcome questions, of course, as we go from our audience, and there are over 900 of you registered, so thank you very much. Please post them on the Q&A box only. That's what I'm going to monitor, and we'll try and answer as many as we can as we go along, and of course, at the end. Now, what are we going to focus on today? Well, I think we're focusing on probably one of the topics of the commercial aviation industry at the moment. That's disruptive propulsion technologies for large commercial aircraft. And I don't think it's an exaggeration to say that achieving a near zero or even a net zero emissions aircraft of over 100 seats is probably the greatest challenge to the current aerospace engineering generation. And I'm delighted to welcome Vince and 3 of his peers who lead teams that are rising to this challenge. So a big welcome today to Frank Haselbach, who's the Senior Vice President and Head of Propulsion Engineering at Airbus. Welcome, Frank. Great to have you.
Hey, good afternoon, Mark. Thanks very much.
Great. You're coming in from Toulouse. Great. Thanks, Frank. I presume.
Yes.
Also to welcome Dr. Martin Stadelbauer, who's the Director Engineering Advanced Programs at MTU Aero Engines. Welcome, Martin.
Thank you very much, Mark. It's a pleasure to be here.
Great. Thank you to have you. You're calling in from Germany, of course. And from Brazil, we've got Murillo Albanese Navas Jr., who's the Chief Technology Officer at Embraer. Murillo, welcome to you as well. Thank you very much for joining.
Thanks for the opportunity. It's a very honor to me to be here with you guys.
Yeah, it's been a real pleasure. And it's great to have Embraer, Airbus and MTU for the first time on one of our webinars. So you are very, very welcome, everybody. We look forward to getting your views and hearing about this. Now, format. We've just decided actually to change the format a little tiny bit just to keep things a little bit different, keep things fresh. We're going to go to experiment with a Dragon's Den style. So each of our experts is going to take 2 minutes to pitch their technology, and then we're going to take another sort of 8 to 10 minutes to debate that technology between us and me answering some questions, or asking some questions from the panel. We won't be having any voting. If you're familiar with Dragon's Den, there won't be any voting, sorry, or any cash that you're going to get that we're going to throw at you for your technologies. But the aim is to probe each technology and test these ideas on offers. And I'm sure, let's just see how it goes. We're experimenting live. So let's open the den. Let's get going. First up for the den is Vince Caldwell from Pratt & Whitney. Vince, over to you. Give us your pitch. And Ellie, I think you've got 1 slide. We're going to have 1 or 2 slides as well. So Vince, over to you.
Good. Thank you, Mark. So let me just start by stating the obvious. Obviously, sustainability is incredibly important to Pratt & Whitney. And Pratt & Whitney is committed to supporting all of our customers in their path to net zero CO2 in 2050. Of course, sustainable aviation fuels are an obvious way to improve the CO2 signature. But the one we can't forget about is making the engines more efficient, right? Quite simply, if they burn less gas, they'll make less emissions. So like we've done for the last several decades, we continue to push the efficiency of the jet engine. And one of the main ways we're doing that is through hybrid electric, right? The Prius of the sky, if you will. And the advantage of hybrid electric is it lets us provide additional power at some key points in the flight envelope, which opens the design space and lets us further optimize the propulsion system and become more efficient. So that's simply what it does. I'll talk about 3 different demonstrators that we're using. The Pratt & Whitney approach is to take very similar and common technologies and demonstrate them across a range of different demo programs to make sure we mature this effectively and as quickly as we can. So I'll start with the one on the left. It's called StepTech. That's sustainable turboelectric power crane technology. This is an experimental facility that's being created at the Raytheon Technologies Research Center in East Hartford, Connecticut. It is a soup to nuts, end-to-end hybrid electric laboratory scale demonstration program. It's in the hundreds of kilowatt class now. It's scalable up to the megawatt class, but it has everything from the heat engine through motor generators, through power electronics and control, electrical storage, through to aerodynamic devices that actually create thrust in a wind tunnel. And it's a way for us to, in a very accelerated way, understand how these entire hybrid electric systems work. We expect that to start running sometime in 2023. Moving to the middle is our regional turboprop demonstrator. This is a 50% hybrid, parallel hybrid electric configuration on a regional turboprop sized aircraft. So it's half the thrust is from a heat engine, half the thrust is from an electrical device. It's a megawatt class electrical device, and we're aiming at 30% efficiency improvement from that. And it ran for the first time on the ground in December, and we expect it to fly in 2024. And then finally on the right is the big one. This is our single aisle class sized hybrid electric demonstrator. It's called Switch, and Switch is one of the new European clean aviation programs. It's a partnership between Pratt & Whitney and Airbus and MTU and Collins Aerospace and GKN, and it will demonstrate hybrid electric technologies in the single aisle class. It will also demonstrate what they call the water enhanced turbofan, which I'm sure my colleague Martin will talk about in a moment. It aims at an efficiency improvement, and it will also demonstrate hybrid electric technologies, parallel hybrid electric technologies in the single aisle class. So everything, this lets us mature our hybrid electric technologies. I do want to stress that hybrid electric technologies are complementary to all of the other technologies we're doing. So propulsive efficiency improvements, thermal efficiency improvements, hybrid electric is complementary to all of them. So it's sort of a natural extension of the GTF architecture, and it's the way we see making our engines more efficient in the future.
Great, Vince, thank you. So hybrid electric, thank you for explaining your vision, your pitch, as it were, your den. And anybody from the group, just chip in as we go. So either Frank Martin or Murillo do. Just explain to us, Vince, obviously hybrid electric, it's incremental. Just discuss how you think about the incremental aspect of it versus other technologies, Vince, because, you know, I suppose what I'm sort of saying is, how radical is it? Is it worth doing in that sense, as opposed to going to say some of the other technologies we're going to hear about at the end? Well,
I don't think it's an either or. I think it's an and conversation, right? If you think about, we can employ a lot of technologies to improve thermal efficiency, a lot of technologies to improve propulsive efficiency, and hybrid electric is additive to all of that, right? Quite simply, think of an electric motor generator that's connected to the turbo machinery that sometimes it draws off power to make electricity and store it, and sometimes it adds power back to the cycle. And what it does is, in typical jet engine design, there are places we have to design the engine for corners of the design space. And the hybrid electric system lets us add power back at some of those design points, but take it away where we have excess power. So it really lets us create a much more optimized gas turbine, even with just a small amount of hybridization.
And would this have happened without the sustainability, the decarbonisation imperative, Vince? I mean, would you be doing this if you didn't have that?
Definitely.
Does it make just sense? Does it make sense efficiency-wise anyway for the turbine?
Absolutely, right. We're always aiming towards making our products more economical for our airline customers. Economical for them means less fuel. Less fuel is also less CO2. So this is the place where the sustainability endeavor and the customer requirements endeavor are locked hand in hand. It's the same objective.
Frank, I noticed did you want to come and make a point?
Yeah, I just wanted to help Vince a little bit in the one point he made. Fundamentally, if you look at it clearly, we wouldn't do hybridization at any cost because we do it in order to make the aircraft overall more fuel efficient. Absolutely. That's the point. You need to get CO2 down. That's one point. And if you look at a specific example, for instance, in cases where you actually have a certain amount of secondary power you need in the aircraft for electrical energy, pneumatic energy, hydraulic energy, and so on, the engine has to run at a certain operating point. If you can help it via sort of electrification a bit, you sort of avoid that you at the same time make a lot of thrust. For instance, if you go in descent, you don't want to have a lot of thrust, but at the same time, you want to have the engine at a certain power level to get the secondary power in a good way. So you have a flight idle challenge, which otherwise actually will generate, you need more drag systems on the aircraft to balance and so on. So there is the complexity of the system is that as you have demand for secondary power, and the engine is the only way to generate that power, you could actually end up in situations where you have too much thrust. If you then actually can balance that with electrification, or sort of slow the fan down because you're actually pulling a little bit out of the LP system and putting it back into the HP system, you can help the overall system. So it's a good thing to do. But of course, it needs to add up at the end because you're putting extra cost, extra system, and extra weight into the aircraft.
Thanks, Frank. Great comment. Vince, did you want to comment back on that?
Yeah, well, Frank's absolutely right. As with every technology, it has to buy its way in. And the engineering challenge and the fun part for us engineers is making sure that we can do these things so they're cost effective and weight effective and maintenance cost effective and all the above. And that's not simple, and it's not simple with any advanced technology. Pratt & Whitney is fortunate that our Raytheon Technology sister division, Collins Aerospace, is sort of the world leader in power electronics. So Raytheon is, I'll say, uniquely positioned to be able to put all these systems together.
Thanks, Vince. Murillo, you wanted to come in with something. Yeah, please do.
Okay, thank you. Yeah, I do want to agree with Vincent. From the aircraft manufacturer perspective, from the manufacturer point of view, the hybrid electric concept makes a lot of sense, since in our perspective, you can size the engine, the gas turbine engine for cruise, for instance, and boost power when you need for takeoff and climbing, for instance, with extra energy. And also, I would add that we can combine in the hybrid electric configuration, we can combine the fuel using sustainable aviation fuel, SAF. So this is a very, in our view, optimized way go through the low emission, the zero emission. So just agreeing with this, that hybrid electric for aircraft manufacturing makes a lot of sense. Of course, it depends on the size of the aircraft, but I do agree with this.
Thanks, Murillo. Great interjection. Thank you. Martin, you want to make a point too?
Yes, that's a question to Vince and maybe to all of the other panelists as well. I would be interested on your view with regard to available battery technology. So what kind of energy densities are you assuming? We have, as of today, something like 200 watt hours per kilogram. Are you thinking about doubling that value, or do you think it's realistic to have a double of that value until 2030 plus, or is that a little bit more of a stretch?
Well, this is the real challenge. And I'll say this very plainly. Pratt & Whitney doesn't make batteries, and we don't intend to make batteries. So it's a bit of a trying to forecast the future, understanding what the power density of batteries is. We think we can make hybrid electric systems effective in the future with even, I'll say, reasonably extrapolated battery technology. Of course, if battery technology gets better, that's, we think, an easy add-on to a hybrid electric system. It just makes it more efficient, makes you could use it further in the flight cycle. But we also need to prepare for something disruptive, right? If there's some miracle out there none of us are aware of yet that makes battery technology a lot more efficient, I think that'll make hybrid electric technology a little more pervasive and more effective.
Anybody, Frank?
Yeah, just put in, so fundamentally clear, you have seen on the Airbus Summit in November, we actually spoke about joint undertaking with Renault to look into actually sort of future battery technologies and so on. So clearly that's on our radar. It's something which we have to tackle. And clearly at the 200 watt hours per kilogram where we are today in cars and so on, that's actually effectively for a land vehicle. If you want to get that into aerospace, you normally actually get a little bit downwards because you have to package it differently. You have to protect it more for several runaway and other things. So clearly you have to target more in the territory of 300, 400 to get to something credible. And that's the journey. That's a journey. That's nothing which will happen tomorrow. And you have to look at the chemistry and the processes and of course the industrialization of that. And of course, if you do all of this, you have to look the end-to-end sustainable and life cycles of emissions of that process. You have that in mind as well.
Yeah, and just on that point, Martin, just I'll come back to you on the question. I mean, some people, when I talk to them for other stories over it, they sort of talk about the batteries maybe being the weak link here as far as aviation is concerned. Is that at the root of your question?
In principle, yes, because at the end it comes down to gravimetric energy density. The better that value gets, the less weight we have to carry around with the airplane, and that's going to be key in the future, I guess. And that's especially if we think about like pure electric aircraft, which are also on the table for maybe very short range applications. That's going directly into the range of those aircraft. So that's where I'm coming from.
Yeah, batteries are big and heavy, but we shouldn't lose sight of the fact there are a lot of other challenges in a large electrical system, right? We're talking about a lot of power. They run at high voltages. There are switching things we have to understand. So I think we can put together good hybrid electric systems, and then as batteries mature, we can integrate those into the systems.
And does that speak to the incrementality of the work that you're doing, Vince, there in terms of understanding these early parts on the journey to get that understanding, to get that technology, to the point where you can actually, fly it, field it, and put it into an operational engine?
That's right. We actually see the systems integration as the real opportunity here, right? And that's why we're running 3 different integrated demos, because we're talking about thermal devices, electrical devices, and aerodynamic devices, all working connected in a very complicated system. So I'm sure there are things we don't know yet, but we're going to learn those through demonstration.
Absolutely. Great. Well, that's fantastic. That's the first den. I think you've passed the test, Vince, if I may say so. Great stuff. Our experiment so far is working. So we're going to go on to the second pitch now. We're going to go over to Martin, who is going to talk to us about, well, now you're going to find out what we're going to... Martin, over to you, please. Thank you.
Thanks a lot, Mark. So Vince already mentioned it. I'm going to talk a little bit more about that water-enhanced turbofan MTU is proposing. Ellie, if you could bring up that slide, would be great. Thanks a lot. Thank you. So here you can see an artist's impression of the latest wet or water-enhanced turbofan configuration, which we are currently investigating. Wet is fully integrated into the nacelle and designed to reduce fuel burn and hence CO2 emissions. And furthermore, we additionally expect significant potential to reduce NOx emissions and contrail formation, which are the 2 major non-CO2 emissions driving climate impact of aviation. And it's also a point I would like to make. If we talk about sustainability in aviation, it's not just talking about fuel burn reduction, it's also talking about non-CO2 emissions and the climate impact they have. Wet is based on Pratt & Whitney's geared turbofan architecture and hence can operate with kerosene or sustainable aviation fuels. And it would be even possible burning hydrogen if that system would be respectively designed for it, of course. Ellie, if you could switch to the next slide, that would be great. So thank you very much. It's coming up. Now maybe one back. Thank you. So this chart, yeah, here we are. This chart shows a very simple schematic view of wet on the upper part and compared to that, a conventional turbofan on the lower part. And as you can see, the first half of wet is very similar to conventional turbomachinery. But in order to increase fuel efficiency, we have added that water enhancement technology behind that gas turbine by using residual heat in a vaporizer, which is placed directly into the exhaust stream, which turns liquid water into overheated steam. A subsequent condenser is then used to condensate that water from the exhaust steam, forming water droplets, of course, which are then being separated from the flow by a water recovery unit. During the condensation and water separation process, we expect soot particles being washed out and filtered out. And furthermore, we can influence the amount of gaseous water content in the exhaust. Both effects give us the opportunity to positively influence contrail formation as well. The water is then being pumped back into the vaporizer, and the steam from the vaporizer is fed through an additional steam turbine on the low spool shaft and then re-injected into the combustion chamber, reducing NOx emissions by at least 80% and closing the water loop. That technology already has been shown and proven in stationary gas turbines already. That concept will be applicable to short, medium, and long-range flights, of course, and therefore it covers almost all the aviation sector's climate impact, which is being generated in those sectors. We are, as Vince already mentioned, working together with Pratt & Whitney, with Collins Aerospace, GKN Aerospace, Airbus, of course, and university and research institutes within that Clean Aviation project SWITCH. SWITCH stands for Sustainable Water Injected Turbofan Comprising Hybrid Electrics. And that's a technology where we bring wet technology and hybridization technology from Pratt & Whitney together into one concept. And they're hoping for synergies which we can harvest there as well. It's a very revolutionary technology, very compelling, very interesting, and tackling all climate relevant emissions, which is from our point of view, the beauty of that project and the beauty of that concept as well. And that would be my pitch, Mark.
Great, Martin, thank you. So my first question, and we'll let everybody come in as well on that, is it sounds fiendishly complex, Martin, which generally means expensive, maybe heavy with other penalties. Obviously, you're thinking about all these things, but just talk through. Wow, you're adding a lot. Seems like you're adding a lot of complexity in there.
I think you're right. Of course, we are adding complexity, and to be honest, we do see a lot of challenges during the maturation of this concept. But on the other hand, I think if we want to cope with sustainable in future, and if we want to make sure that we reach something like climate neutral aviation, we need a concept which of course reduces carbon dioxide emissions. And that's not going to be easy, of course. We already had that very, very big step of the geared turbofan from Pratt & Whitney bringing us 16%, which is like a quantum leap in efficiency, of course. But going further, there is still a lot of possibilities there, but going much further, I think you will also need revolutionary technologies, and that's where you're gonna have more complex systems. And furthermore, if you want to tackle not just CO2 emissions and fuel efficiency, there is the need to do something else, and that's exactly where wet comes in. And I would think, okay, yes, we are adding complexity, we are adding maybe operating cost and weight as well. That's for sure. But on the other hand, you're getting a better fuel burn efficiency. You're getting a much more sustainable aviation with that. And if you suppose that, at least in the future, if climate change is gaining much more momentum as it does as of today, and politics starts to react, you want to have new and revolutionary technologies together with sustainable aviation fuels, giving you the opportunity to honestly say we are reaching something like climate neutral flying. And that's our goal here.
Okay, so I've got a question coming in from the floor, Martin, saying Rolls-Royce employed anonymous attendees, so I don't know who, since the 1980s, the water-enhanced turbofan. What improvement is here compared to what Rolls-Royce did? I don't know if they have, but presumably that person knows what they're talking about. What's your thought?
I'm not aware of a technology where you in-flight recover water from a turbo machinery. So the beauty of that concept here is, with compared to what we know from the past, is we are not just injecting water into the combustion chamber, but we are recovering the water from the combustion process with those vaporizer and condensation units and putting it back into the cycle. And that's where the water comes from. So you don't have to carry a lot of water with you, maybe during takeoff and climb phases, but that's it. And after that, the cycle runs on its own.
Okay.
Yeah, and historically, jet engines have used water injection on takeoff for power boost. I mean, that happened in the 60s, right? It's not really done anymore because it's not terribly efficient, but it is historically accurate.
And to be fair, industrial gas turbines have used it for emission management as well.
Right.
So,
absolutely, yes. Yeah.
So those are the two things you actually do, because you get more homogeneous combustion sort of temperature distributions and consequently better NOx emissions from it. So all of that is there. I think the comment from Rolls-Royce was more on the typical sort of power boost for takeoff on military or defense applications.
Right.
Maybe, Mark, if you allow me, as I'm speaking, I think maybe just to explain, clearly Airbus is a partner together with Pratt and MTU in all of this. And we looked at this, and I take a more philosophical sort of approach to all of this. You know, the wet engine on hybridization is fundamentally, the wet engine is waste heat recovery, bringing it back into the cycle. So it's effectively, you could argue, thermal cycle improvement. We're also looking at other concepts. For instance, together with CFM, we're looking at the open fan, which is pure propulsive efficiency improvement. In fact, you're sort of taking the weight out of the system, making a very big fan, taking a casing away. That's one way of doing it. Allows a lot of improvement. Or you say, I stay with the traditional turbofan. I have the sleek lines and the nacelle and so on, but I use some of the nacelle to manage all of that sort of heat exchange. And in fact, we go for thermal cycle efficiency. Both will actually give fuel efficiency to the system. Both have their pros and cons. Both have a journey to do. And, as Airbus, we have decided we're going to work on both systems and understand, the pros and cons of them in order to see what actually is the right choice for the next generation aircraft in terms of propulsion technology, which allows to do at least a third of the journey to net zero carbon at 2050. So consequently, I think it's all consistent in that approach.
Great.
Fine.
Maybe
Martin, do you want to come back on that?
Yes, if I'm allowed to weigh in here, Frank, you absolutely correctly mentioned stationary gas turbines with those Cheng cycles, which already do that kind of stuff in the water recovery. I think the challenge here for the flying application, of course, is to get the sizes of heat exchangers and vaporizers to a scale and to a weight level where you really can cope with during flying applications. That's going to be the biggest challenge here. There are, of course, a lot of other challenges as well, but it's going to be a very interesting technology challenge during the next 10 years, I would say.
Weight and drag will be the key challenge because it doesn't help you if you have a super efficient engine which doesn't generate drag.
Absolutely, yes.
So
absolutely, yes. Yeah.
Right. Mark, I have a couple things to add. So yes. The first is you talked about weight and complexity, but if we take the historical view, every jump in engine efficiency has come with more weight and more complexity, right? Turbofans to low bypass ratio high to gears to, things like wet. So we add weight and we add complexity, but we do it for efficiency, right? And I think that trend will continue. The other thing I'd like to reinforce is I think Martin mentioned non-CO2 emissions. And I think that's a very important part of the conversation that's just starting to emerge, right? We have to talk about contrails. We have to talk about other emissions at altitude. And I'll say the science behind their impacts, how jet engines impact those and how those impact the environment are not quite as mature as CO2 impacts. But I think it's something that will be a bigger piece of what we do in the advanced propulsion world going forward.
No, great points. Excellent. Thank you very much. I think that's probably, there are some comments about, we've talked a little bit about the weight penalties, which is coming into the box. There's also, somebody's talking about the length of the power plant, managing the extracted particulates is from David. Thank you, David, for your contributions. Do you want to just talk to those or just add anything more, Martin?
Yes, in terms of weight, of course, there is a weight penalty. We are talking about 40% weight increase compared to a same level of technology turbofan in the future. And it's also completely right that the nacelle is going to be longer. That's also true. So drag is going to increase. From all what we know from our current analysis, we think there is still a very big benefit in terms of fuel burn if you take all those effects into account. Of course, during that switch project in the first phase of clean aviation, we are going to assess that in much more detail and also trying to understand the aircraft integration effects. But yes, it's going to be longer, it's going to be heavier, but we are still convinced that the overall benefit in terms of fuel burn efficiency is going to be quite substantial amount, I guess.
Great, thank you, Martin. Just talk about the transition from using SAF or Jet A1 to potentially hydrogen in this kind of technology.
Of course. Well, it will be, as I guess every future gas turbine will be 100% certified for 100% usage of SAF. I think that's clear, and the technology step there is not really big, to be honest. But in terms of hydrogen, there will be some more design work to do, of course. You're going to have to design the combustion chamber to be able to cope with hydrogen, to burn hydrogen. But on the other side, you're going to have a very big advantage because as we think hydrogen as of today, and Airbus, I guess, has a much clearer view on that with their ZEROe program, it's going to be stored in liquid and cryogenic form within the airplane. And that gives you, especially for something like a concept, the possibility to use that cooling potential in order to make the size of the heat exchangers much smaller. So I think that's another beauty of that concept.
Right. Any final comments before we move to the next dragon? No, I think we're good. Martin, great. Well, so we've had a great look at hybrid, electric, with Vince. Now we've had the enhanced turbofan with the water there, maybe hydrogen at a future point. Great. So that's some of the best propulsion technology we have on offer. Thank you, gentlemen. Let's go on to our next dragon, which is Frank. We've already heard quite a bit from you, Frank, but we are going to talk about what Airbus is betting on. Go ahead, floor is yours, sir.
Absolutely. Thank you, Mark. So it was the last time I was called a dragon. It's a little bit of time going by. I hope we're going just to the next den, actually. But here we go. So what you see here, I won't have any sort of big charts. What I sort of actually put there is what we've shown to the world a little bit more than a couple of years ago. Effectively, our sort of concepts for hydrogen-powered aircraft. And so, we're looking at effectively 3 aircraft concepts, and that is over and above all the activities we're doing with all engine manufacturers, whether it's Pratt & Whitney, MTU, CFM, or Rolls-Royce, in looking at various sort of options for making the next generation aircraft more fuel efficient, getting step changes in aircraft technology, either by higher bypass ratios and higher propulsive efficiency, or by better thermal efficiency, open fan, switch, UHBRs, or you name it. So that's fundamentally step number 1, get next generation aircraft ready. However, over and above that, at Airbus, we believe if we are serious about getting to net zero carbon in 2050, we have to have more. And that more is effectively a concept of going with an energy carrier, which hydrogen is, which is completely carbon free, which also sort of thereby avoids, besides CO2, also some of the other sort of non-CO2 effects, because you can actually have hydrogen hybrid electric approaches where you actually have very low temperatures and you manage without any NOx emissions, but you still have water emissions and so on. So that's one of the reasons. The other one, we also thought about the energy you need to get then aviation flying. If you look at this, fundamentally, you want to have green energy. So you want to have the lowest amount of energy used to get to an energy carrier, which you can use in an aircraft. Hydrogen is definitely one of those, because if you want to go to synthetic fuel, you need to do over and above that also capturing of CO2, Fischer-Tropsching of fuel, making some aromatics, and getting effectively a drop in sustainable aviation fuel. It has its place, but it takes more energy than hydrogen to be generated in the first place. Of course, hydrogen itself has some challenges and has some opportunities. It is a much more energy dense per kilogram, less energy dense per volumetric than Jet A1. And that's one of the reasons why in our concept we're looking at liquid hydrogen storage, because that's about double the volumetric energy density than gaseous, which other sort of companies pursue. And if you look through the concepts you see here, you see a turbofan aircraft and a turboprop aircraft, which could also be something like an hydrogen hybrid electric powertrain, so partly sort of hybrid electric or fully hybrid electric. And the rear part of the aircraft you see on the left is sort of dark blue. It's a nice indicator for this is where the hydrogen would be stored, not in the wing like Jet A1. It would be in the back, because you need to have spherical or cylindrical sort of tanks, which at pressure slightly above ambient, let's say 2 bar, you effectively sort of put this at cryogenic conditions, so minus 253 degrees Celsius, you have the liquid hydrogen, and then you actually have a distribution towards the engines. On the propulsion side, you either just effectively burn the hydrogen in a normal turbofan, and there are certain modifications you need to do to a normal turbofan engine for that, but not much. It's doable today. And we have seen that, and that was demonstrated by various companies throughout the years. And of course, you can also do this in a turbofan. You can do this in a turboprop, which is effectively a gas generator with a gearbox and a propeller. Or you could effectively have a fuel cell, which is feeding into sort of an electric powertrain and eventually drives a propeller. Benefits on propellers and turboprops, of course, is high specific thrust at zero speed, at takeoff, and you therefore bring the power requirement, energy requirement down for the takeoff condition. On the very right, you see an aircraft which is a blended wing, which clearly actually brings a lot of sort of extra sort of novelty to all of this. It's unlikely, most likely, that we go with this as a first concept aircraft, having in mind we're changing the energy carrier, we're modifying the propulsion concepts, then to come at the same time with a completely new aircraft aerodynamic and weight and balance concept and so on would be a challenge. However, if you look at the volumetric situation of that aircraft, it allows nice places to store the hydrogen, has a good and sleek integration of the engines, and therefore makes some sense. So that's where we are, and clearly we are on the one hand side fostering all the ecosystem around hydrogen management in the airports with the airlines, the ecosystem overall, but also we are clearly sort of working with our partners from the engine companies to make sure that we actually have good things and technology bricks to come there. We're going down a route of doing demonstrators. We've been very vocal about our open fan demonstrator, our hydrogen H2 combustion demonstrator together with CFM, and the demonstration of an hydrogen hybrid electric powertrain on our A380 flight test demonstrator vehicles, where we have two of. So I'll leave it there. I think it's sure there will be a lot of questions around this, but I'm open for any discussions.
Thank you, Frank. Great stuff. Well, my first question, and I asked you this yesterday when we had a pre-chat, but let's just get it out there as well, Frank. Is it you've got in this panel, you've got two very smart engine companies, and yet Airbus is doing a lot of this propulsion work yourselves, and I'm kind of thinking to myself, why? Why are you doing that? You've got you talk about fostering, but just talk us that thinking.
I think it's a little bit more than fostering on some areas. It's clearly stimulating.
Well, you're doing the hydrogen fuel cell development yourselves, aren't you?
Yes, we do. We have a joint venture there on the one hand side, and that is effectively just the means to get the electrical power, and then of course you need the motors, the power management, the gearbox, the propellers, and all that sort of stuff. And clearly, we're looking at all of these technology bricks, also the thermal management for all of this, and we were simply we looked at the calendar. To be fair, Mark, if I look at the calendar, it's less than 10,000 days to 2050. It's 9,795 today. I just checked that. So fundamentally, it is not much time. And we're actually losing time by sort of carefully going down this route. We're seeing some companies which we're really actually happy about driving, quite fast into this with approaches where we feel we need to have a little bit more technology bricks on the way. So what we actually said is, well, let's start the process at Airbus. Look at this. It's effectively a different concept than a gas turbine. So you can actually sort of say, well, how do we integrate all of this? Can we actually achieve that? We are inviting partners all the time, but we're very, very keen to sort of advance the technology. So at the end of the day, if you look at an overall hydrogen-powered aircraft, you would most likely also have the secondary power for starting up the aircraft, setting like a fuel cell or something like that, because you wouldn't have in the back sitting an APU which is running on Jet A1. Doesn't make any sense. So all of these things clearly actually gives for us to say, well, there's a huge a target-rich environment of actually getting new technologies in, understanding them, accelerating them, and if we're taking part in that, well, that's good. That's just generating pace, and that's what we want, pace.
Pace, great. Any of the panelists want to come in on that before I jump in with a question myself? Well, yeah, go ahead, Vince, then Martin.
Yeah, I'll dive in. So first of all, we're excited about hydrogen, and I'm glad to hear Airbus talking about the infrastructure and the airframe, because whenever we talk about hydrogen, I caveat it with, well, someone has to make an airplane that has hydrogen on it, and someone has to make an airport that has hydrogen. But given those things exist, there are huge thermodynamic advantages in having cryogenic hydrogen, right? Quite simply, you have a fuel that has a very, very cold temperature, so you now have a thermodynamic cold sink. It enables heat recovery in the exhaust. Heat recovery in the exhaust makes you less sensitive to aerodynamic losses in the cycle. Burning hydrogen also makes a lot of water, so it makes water recovery possible. So you can do steam injection, which increases specific power of the core. You can do intercooling, which decouples OPER and T3, and it essentially unlocks thermodynamic efficiency we can't do today. So recognizing there's a lot of engineering involved to make all that happen, but thermodynamically, hydrogen is a wonderful fuel. And we're doing an ARPA-E Department of Energy study now called HySite that says about 35% improved efficiency with the hydrogen engine versus today's single aisle. So we see huge opportunities.
I agree.
Thank you for that, Vince. Frank, or do you want to come back, or Martin?
Yeah, maybe just one comment to your question to Frank with regard to a propulsion system integration at Airbus. I think all those new revolutionary concepts, be it an open fan or wet or whatever, and of course also hydrogen, they all will have to closely work together with the airframer, because all of these concepts need some major adjustments to what we know of airplanes as of today. And that's also, I think, a very interesting perspective, because all that sustainability topic for as of today and also in the future will pave the way to new ways of cooperating and to new corporations.
Yeah, thank you, Martin. So we might pick up on that later as well. Murillo, yes, please go ahead.
Yeah, I just would like to also add here that I see a lot of challenges for the hydrogen. One of them that was mentioned here is the ecosystem. So how we produce all the required hydrogen and how we store all the hydrogen and how we will support all the infrastructure in the airport. So I'm really happy to hear that in fact, Frank mentioned that the ecosystem needs to be involved as well. In terms of the size of the airplane, I do think in Embraer thinks that for bigger airplanes, the hydrogen it's a very good opportunity for having the new future of sources of power energy. And I would like to ask Frank about how does he see the possibility to use dual fuel use. I mean, you have the capability in the engine to use the hydrogen, and at the same time, since we have more density with the Jet 1 or the SAF, we can also use the SAF for different phase of use or use it as a reserve for fuel. It's a question.
Well, that's an interesting question. We actually had discussed that inside Airbus as well. So fundamentally, we're looking at that and saying, well, if I go all the complexity of sort of getting the technology bricks ready for sort of storing cryogenic hydrogen, distributing it in the aircraft, preparing it for combusting in the engine, which means I need to have, of course, a vaporizer somewhere to get it from liquid back to gaseous and so on. So there's very little logic for us to actually add, effectively, an additional sort of traditional Jet A1 system and so on, because we're just fundamentally actually getting a little bit more. So we can store a lot of energy in the aircraft already with hydrogen. So I don't see that problem. If we were in gaseous, that might be a different situation, because then you have twice the volumetric sort of requirement, and you fear that you're not getting enough packs or cargo in, and you might want to go with a little bit of Jet A1 and a parallel one. But in that world, I would actually stay at pure hydrogen or hydrogen hybrid electric. I can see that.
Great, thank you, Murillo, for the question. Thank you, Frank. Right, that's Frank's den. Thank you. You've managed to come out unscathed there, Frank. In fact, you've actually ripped it all up. So, Murillo from Embraer, let's go to your pitch. Let's go. We're running hard on time, but you've got your 2 minutes, sir.
Okay. Well, my peers here, my friends, they will make my job easier, since they have already covered a lot of those subjects. So I don't need to cover all how it is today imperative to go through sustainability in aviation. And I would just add that together with the challenges, we have huge opportunities, not only for new products and how we will serve the world, but also opportunities for all the supply chain opportunities for the aviation. So we can go for the next slide, since my friends have already covered those topics here. Next, please.
Yeah, just carry on as well, Murillo. It'll change over. Ellie will just change it over so you can continue with your pitch.
Mm-hmm.
Can you go to the next slide, Ellie, if you can hear us? Murillo, why don't you continue with your discussion so that we can catch up on the slides while we go?
Perfect, no problem at all. Yes. we do foresee, since Embraer, we're planning the future for our products, since 9-seat aircraft to more than 150 aircraft that we have today. So we do not see, in our view, for the clean aviation, for the net zero aviation, we don't see a silver bullet. We see opportunity with the hydrogen as well as challenges, as mentioned by Frank. We see electric propulsion, and here we include the hybrid concepts. Here's just our demonstrator that we have flown using full flight with electric power. SAF, we see a huge opportunity since we have a fleet over there. So we will not change all the aircraft that are already flying by 2050. So we need to use SAF, definitely. And one point that is very important, especially for urban air mobility, that we are very focused in, is also noise reduction. We need to take care about noise, especially if we want to have vehicles flying in our cities. And recycling, definitely, thinking about new materials and more sustainable materials, that's key for our view. We have already presented, and I'm not bringing here, but I'm pretty sure you're very familiar with the Energia family, where we have concepts that represent our challenges. So we have a fully electric aircraft, we have a hybrid electric concept as well, we have a hydrogen using fuel cells, and we have a direct use of the hydrogen in the gas turbine. So we don't foresee, I agree with my friends here. The idea is that we don't foresee only one solution. We see that each solution will be customized. The mission and the size of the airplane will design the perfect, of the optimized solution for each size of the airplane. So that's our view. And Embraer believes that we have to be focusing all those, improving together with the ecosystem mentioned by Frank in all these opportunities. We don't think that the hydrogen is the best solution for a 10-seat aircraft. We don't believe that fully electric is a solution for a 100-seat airplane. So we need to do all the trade-offs and take into account all these opportunities in the world now. Next slide, please. And from the point of view of airframe manufacturer, we do have to see the low emission or the zero emission as a combination, as a partnership with not only the ultra efficient propulsion that was mentioned here by Pratt, by MTU, and we fully agree. Not only that, but also with ultra efficient airframes. So when we take an airframe existing in the market and then we put hydrogen on it, we're not taking advantage of the all possibilities. So we do think that the airframe needs to be customized and to be constructed together with the new technologies. And definitely the integration, my peers also have mentioned here about the challenges, the weight, the drag, the thermal management. Those are very, very challenges, issues that we have to go through. Regarding batteries, not only the power density or the energy density, we have also to take care about the cost of the batteries. That's a key issue for the engine, for the aircraft manufacturer. The life cycle of the battery is also an issue for us. We need to take care of all that. With the hydrogen, we have to take care about the green hydrogen. So if you take the hydrogen using fossil sources of energy, it will not help at all. So this is it's an integration of all that, and the challenges is not only technological challenges, as I mentioned. We need to have solutions that are economically feasible. Definitely, the clients are looking for something that makes sense economically saying. Infrastructure and supply chain, that was mentioned by Frank, we fully agree. Policies and regulations. Also, with all the authorities, we have to work together with those partners. And public acceptance, having vehicles flying the urban air mobility, single pilot, and things like that, that will help also the zero emission in the future. Those are critical points that we need to involve as the society as well. So this is my pitch, taking advantage of what my friends have already mentioned here. I'm open for questions.
Great, thank you. Really great stuff. Just develop a little bit more for me. You know, what is an ultra efficient airframe in your view? I mean, Frank sort of said, look, the blended wing body maybe not going to be the first one. What's your thought?
Yeah, I do see that the engines are changing the size, the amount of bleed that they are requiring, open rotors or distribution, propulsion, things like that. And maybe the optimum solution will not be anymore a tube and a wing, as mentioned by Frank. We think that we need to also look for different configurations, truss-braced wings or joint wings, wing body configurations, how we will store the hydrogen or the batteries, for instance. So this is a optimized integration. How we will take care of the heat produced by the fuel cells, or it's a lot. 50% of the energy from the fuel cell will go through heat. How you dissipate that heat? So it's an integration airframe together with those challenges. That's my view, Mark.
Okay. Does anybody want to come in on that, or shall I go into the next one? Frank, did you want to come in?
Maybe just to comment. So clearly, we spoke about disruptive propulsion here today. Clearly, there's a lot of other stuff which is happening in the system. We're looking at wings, we're looking at materials, we're looking at all sorts of stuff which will drive, let's say, more efficient aircraft. So that's absolutely clear. But if we look at the propulsion concepts, and I think it was very well said by the other sort of panelists here, they're getting more and more important that they're integrated well in the aircraft, and that's why Airbus is focusing so much on this, and this is most likely why Embraer is focusing so much on this. Because if you do an aircraft, you can't just go and say, no, I want this engine. You have to sort of, if you really want to have another 10, 20, 30% step change in fuel efficiency, you have to do far more. And as you're changing energy carriers and a lot of other questions in there, it just gets a completely different feast. And that's why we're doing all of this now together in order to be ready for the middle of next decade. It's still, yes, it's still some years away, but as we know, it's less than 10,000 days to 2050. So we have to get going. If I look at the thermal challenges, I think that was what Murillo just mentioned quite nicely. Clearly, hybrid electric has thermal management challenges. Fuel cells have thermal management challenges. Engines, jet engines today, whether they burn hydrogen or sustainable aviation fuel, have their thermal management built in. Air goes in the front and comes out the back hotter. So it's gone. So it's easier in that respect. So you have more complexity in actually managing this. And that needs to be lightweight, foolproof, needs to work, needs to be sort of in good condition and make sense overall in the system. So this is where all the integration challenge comes from.
Yeah, and we cannot forget about the economical feasibility as well. It cannot be too much expensive. That's true, Frank.
Yeah.
No, absolutely. Well said. Okay, so anybody else want to come in on any of Murillo's comments at the moment?
Well, I would make one quick comment. So Murillo was the first one to mention sustainable aviation fuel. Thank you for that. We can't lose sight of the fact that SAF is the silver bullet, right? For most of us, we have a huge installed base out there now. And the most important thing we can do to decrease our CO2 impact is to burn SAF. Now, none of us on the phone make SAF, so I think our job is to continue to work with and lobby the fuels industry to increase their SAF capacity. But it is the most impactful thing we can do right now.
Right. No, absolutely.
Especially for the flying fleet. Absolutely. There's no debate.
Yes, absolutely.
Yeah, I mean, what's the installed fleet? 25,000 plus, something like that?
Yeah, in that territory, yeah.
Yeah. It's a lot of metal out there, a lot of people flying, and that's just current. And we know what the production rate of Airbus is and Boeing, etc., and Embraer. You know, we're adding aircraft continuously. We have a lot of open questions. So we've had our den. Thank you very much, everybody. I think that's worked quite well. We'll see. Let's see if we can tackle a few questions. We haven't got a lot of time, but try and keep your answers short, guys, if we can. Let's talk about certification. Just briefly, that ecosystem, that's not an ecosystem, that's going to have to be developed as well for hydrogen. What are the big challenges, Frank?
Well,
that was from Emmanuel Gianotti, by the way.
Decisions like, do you sort of produce and store at the airport or not? How does the whole sort of fueling work? So how do you manage the safety around the airport? How do you effectively make sure that you are generating green hydrogen and not having sort of fossil or gray hydrogen coming in some way? So there's an element of let's say, society needs to help with regulations and incentivization of all of this, of course, in the bigger picture. If I look at certification, clearly we're in the phase of exploring. We are in the phase of actually getting the TRL level up. We're actually going up, and let's face it, in hydrogen terminology, we might be in the area of tier level 2, 3, 4, depending on where things are. So we are not there at being product ready. So we're working together, of course, then with the regulators. Whilst we are understanding more, we will show and demonstrate how is this safe, because clearly safety is non-negotiable, and the product will always be, the next product will always be as safe or safer than the one before. Oh. So you have to actually go down this learning curve and take the regulator with you. And they will actually take their role in that process very, very serious, and make sure that we are all together marching in the right direction. So I don't see any big challenges there. Technologically, all of that is doable, but it will take time, it will take effort, it will take money, and it will take a lot of people doing it in parallel. And that's what we're trying to push.
I think that's an important point we made in the preamble, was that the new partnerships that are being developed, the new bedfellows that are being produced here to make all this work, certification being one. Martin, just comment, or Vince, just talk about how this sort of technological ecosystem is developing, because we're seeing all sorts of names pop up that you think, I never even knew they messed around in this area. What's going on there?
Yeah, it's actually quite interesting, and it's much more integrated than it used to be. I mean, a lot of aviation history has been sort of commodity based, right? You know, someone buys a piece, you plug it in and you go do something. Well, with these much more integrated systems, it really has to be developed in a partnership at a system level, right? And it's going to raise some interesting questions about, you know, what is a propulsion system now if batteries are inside the fuselage and things like that. So there are some control volume questions that we have to deal with, both from a certification basis and I think from a business basis. But the more integration also is where advantage lies, right? Because more integration means there's better opportunity to now co-optimize and get better performance out of a system.
And also you're bringing in new technologies, and those new technologies are causing new corporations as well. And for example, that Switch project is one example for that. We have a very mighty consortium which covers like 11 countries over the US and Europe. Of course, we have companies like Collins Aerospace here on the table as well, dealing with hybridization of the GTF and brick technologies for that. So as long as you bring in new technologies, you also start new corporations. I think that's also a very important key here.
Yeah, absolutely. Frank, did you want to come in here?
No, I think I said most of the stuff I actually wanted to get across.
Okay,
I think for me, the key, maybe one thing to sit back and ask ourselves. So in the next, and I think we had that discussion yesterday, Mark. So in 20 years from now, the society will decide of how sustainable aviation is, how sustainable it needs to be in order to sort of be a viable and allowed mode of transport. And that's what we really need to be conscious of altogether. So fundamentally, I think all the stuff we're doing together will drive a more sustainable aviation. I'm absolutely convinced. It will be always a combination of new technology on the propulsion side to drive more fuel efficiency, then a good portion of sustainable aviation fuels, which have to be clearly on the one hand side, either biofeedstock or synthetic, which means a lot of renewable energy needs to go into produce aviation energy carriers, which is a societal challenge, let's face it. And then, of course, last but not least, the new technology of integrating all of that in aircraft and making sure that you can actually have a safer than today, better than today, and more cleaner than today sort of way of flying. So that's where I am.
That's a great, I think we're going to use that as our bookend there, Frank. Thank you so much for that. We're right on the dot for time. So I'll just summarize. And also perhaps what I'd like to invite this panel, maybe you add one or two others. Let's come back in a year's time and see how far we've got on our thinking. Absolutely. Because that would be really quite fascinating too, right? Open invitation. Yep. Thank you for your great contributions, everybody. Martin, Frank, Vince, Marilia, absolutely brilliant. I trust the Dragon's Den concept has just added little bit of spice to the format. Sorry that we haven't got to more questions. There's a lot of questions down there. I've had to manage that on my own, so apologies for not getting too many. But thank you to everybody for being on the webinar. Thank you to Pratt, obviously Pratt & Whitney, for sponsoring. I've got to do a final little advert for FlightGlobal Premium, because I tell you what, if you're doing daily aviation news and analysis, FlightGlobal Premium is top. Obviously I used to work for FlightGlobal. I still do work with the FlightGlobal team. It's brilliant, and they're offering you all a 20% discount if you join this webinar, and it's a really valuable tool in your workflow there. You know, it makes sense, right? This webinar will be available on demand shortly. Our next one is going to be on the topic of disruptive technologies for advanced air mobility. It's going to be on the 18th of May, and there's been quite a few questions about that in the stream as well. So look out for that. Make a little diary note. Again, we're a bit over time. Do apologise again for the questions. We got a lot of great input. Thank you. Again, thank you to all of our panelists. I wish you all a very good day, and goodbye until next time from me, Mark Pilling, and from FlightGlobal. Thank you very much, everybody. Bye-bye.
Thank you.
Thank you, Mark.
Thank you. Bye-bye.
Thanks a lot.
Thank you, guys.
Thank you, Mark. Thank you.
Yes, see you.